Hey guys, I guess you thought you'd had a break from me, but no, you don't. There's probably someone else in the room who could weigh in on this just as much as I could. We don't get too much farther into kinetic molecular theory than regular chemistry does. Kinetic molecular theory is a way of looking at how particles move, and my suggestion is that you actually imagine you and all of your classmates are gas particles, and how would you move around the room? You certainly wouldn't be sitting still. No, I don't want you to get up and start slamming into each other right now. That would be disastrous and would not be exactly what we want here. So it's our attempt to explain how gases interact with each other. Now, we're going to separate gases into two categories from the get-go. First of all, we are pretending that these gases are ideal. That is probably a lie, but we're going to pretend they're ideal. An ideal gas is non-polar. Alright? Oh look, it's underlined. An ideal gas should be non-polar and relatively light in mass. Why can't I get the underline to go? There we go. And relatively light in mass. You want a non-polar light gas. The smallest, lightest non-polar gas in the entire planet is definitely helium. Why not hydrogen? Hydrogen H2 should be non-polar in a lot of people's minds, but it does have a charge on it, kind of. Think about when two hydrogens bond together, you have a proton and one electron, and they bond, and the electrons are actually stuck in the middle of the two protons for the most part. We'll talk about bonding and anti-bonding orbitals later in the year. But for the most part, the electron is stuck between the two nuclei. Then you have these positive charges on the outside, and it's kind of a weird molecule, H2. But helium, however, helium has two protons in the nucleus where they belong, two electrons flying around the outside. Incredibly light mass. It makes a very good ideal gas. As you get heavier and heavier, even if it's non-polar, it starts to misbehave. So, in kinetic molecular theory, we pretend that none of the gases misbehave. But let's talk about a gas that definitely misbehaves. Water. H2O. Can it be a gas? Yes. Does it always follow the gas rules? No. It does not follow the gas laws all the time. I can think of a number of instances as I drink this water right now that it does not always behave as water, as a gas. Why does it not behave as gas? It's polar. It's actually very polar, and that means it's not a very good gas. But let's just talk about KMT for a second. So, first of all, we pretend the volume of the particles are assumed to be infinitely small and not worth mentioning. We assume that the volume of a gas is equal to practically zero. Particles are in constant motion. They're always flying around, slamming into each other. That when those particles collide with a container, we have the force times the mass, the acceleration. That mass times acceleration is exerted on an area. We call that force, mass, acceleration over an area pressure. Particles are assumed to exert no force on each other. When two non-polar molecules collide, those two non-polar molecules have no interest in each other. So they would just bounce right off of each other. And then the average kinetic energy of a collection of gas particles is proportional to its Kelvin temperature. So here are two kinetic energy equations. The average kinetic energy. Kinetic energy average per mole. So if there's a per mole component in there, it's 3/2 RT. So 3/2 times R times T. Immediate note right below, for those of you who are wondering which R value to pick, it says it right here. The R value for this equation is the kilopascals version. Notice that the kilopascals has been replaced with a J. J is for joules. The conversion from joules to kilopascals is a 1-to-1 switch. It's pretty nice. Yeah. So as the temperature is changed, the kinetic energy of the gas particles is changed. They are directly proportional. If the temperature drops to 0, then the motion drops to 0. The kinetic energy drops to 0. Interesting. Let's see. Then we have the other kinetic energy equation, slightly different. This one relates kinetic energy to the mass, or molar mass of the particle, and the velocity. When we're actually talking about individual particles, maybe we shouldn't say molar mass. We should probably be saying atomic mass units. So the atomic mass unit for helium is 4. The atomic mass unit for O2 is 32. Therefore, oxygen has an atomic mass that is 8 times heavier than helium. There are some implications there, which we're going to get to on the next page. If you have a balloon of helium and a balloon of oxygen, and they're filled up all the way the same, they'd be at the same temperature, possibly, which means they'd have the same kinetic energy. If they have the same kinetic energy, that does not mean the particles are moving at the same velocity. Their masses could be different. And Max Boltzmann has a distribution curve that kind of discusses just this. It's the velocity of the particles. Well, this one actually is, the way this is drawn is for let me just read this. Oh yeah, if mass is being represented, then the heavier the mass, the slower the velocity of the particles. The lighter the mass, the higher the average velocity. And this is a distribution curve. We're not saying that every C particle, whatever that is going to be here. You're going to have some that are moving drastically faster than others, but the average of C is going to be a lot higher. Let's just throw some elements up here. Let's say that this is helium, helium being the lightest. Let's say that this is oxygen. And then let's say that this is chlorine. All three of these are nonpolar gases. They should behave like gases very well. If they're at the same temperature, let's go back to that other equation. If they're at the same temperature, 3/2 RT, they're all at the same temperature, their kinetic energy would be the same. They would be moving through the space with the same amount of energy. If their temperature is the same, they'd be moving with the same kinetic energy. On the other side of it, though, if their kinetic energy is the same, that doesn't mean these two values are equal for all three species. In fact, the molar mass of helium being 4 means its velocity has to be a lot faster to achieve Ke. Oxygen being 32, its mass is 8 times heavier, so its velocity can be a lot slower. Chlorine, 70, so since it's double oxygen, its velocity can be a lot slower and still have the same kinetic energy. The other thing this Max Boltzmann distribution curve could represent is, let me just could also be used to represent a substance at different temperatures. Let's say that you have 3 samples of chlorine gas, and instead of being at the same temperature, you have a cold sample of chlorine, 0 degrees Celsius, a warm sample of chlorine, 50 degrees Celsius, and a hot one at 100 degrees Celsius. The distribution of particles would vary because they're at a different temperature. Go back. If they're at 3 different temperatures, you'd have 3 different kinetic energies. These kinetic energies would have the same mass because it's chlorine, chlorine, and chlorine, but the velocities would have to make up the difference. So for the hottest particle, it's going to be moving the fastest. And I have a very pretty version of the same thing right here. Is the relative number of particles moving at room temperature. At room temperature, you can see hydrogen is moving the fastest of them, just merely because it has the lightest mass, and it moves on down to there. And this distribution is totally related to the mass. They're all at the same temperature, so the same kinetic energy, and as their masses vary, so do their velocities. Alrighty, that is actually all we're going to talk about right now. When I come back, we're going to talk about diffusion, effusion, and we're going to talk about deviations from the ideal gas law. Now it's time to get ready for your quiz.